All right, guys, I'm sorry about class today. My son Leo is sick, so it was my turn to stay home with him. Yeah, you're probably going to hear him during this lecture. Yeah, he's yelling Elmo right now if you can't understand that. So hold on, I'll be right back. All right, so we're going to finish up 2.5. I should be able to get through all the notes here. And then the fun sheet will be posted on Canvas. We'll probably do the fun sheet on Tuesday. Hopefully I'll be there tomorrow. But let's go ahead and start talking about this. So remember limits at infinity. Basically what we're talking about when we're talking about limits at infinity is we are talking about the behavior, we're going to call it end behavior of a function. So we talked about when we have something like 1 over x. This is not a perfect drawing. What in life is, though, right? We've already looked at that the limit as x approaches 0 from the right of this function. So we've talked about infinite limits. That was infinity, right? And we know that the limit as x approaches 0 from the left of this function then is minus infinity. So this is the topic here in 2.5 is a little bit different than that. What we're looking at now is not infinite limits, where when I approach a number for x, my function increases or decreases without bound. But now we're looking at, so what's happening as x gets big? So as we look as x goes to infinity, can we describe the behavior of the function? Does the limit exist? Sometimes it will, sometimes it won't. But in this case, it does, okay? So the limit as x approaches infinity of 1 over x, we can see it's going to 0. And we're going to see that this is true anytime we have 1 over something that's growing really, really big positively or really, really big negatively, we're going to go to 0. So likewise, the other side, the limit as x approaches minus infinity of this 1 over x is also 0. It's just as we look at x as it approaches minus infinity, we're just heading to 0 from the negative side. I want you to know, though, that these guys are not always going to be the same. So the limit as I take x going to infinity and the limit as x goes to minus infinity or negative infinity are not always going to be equal, and we'll look at some examples of that. If you remember in class on Friday, we looked at tangent inverse, and remember tangent inverse, which is the inverse of tangent, as we all remember, does something like this. Okay, where if you look as x goes to infinity or theta goes to infinity, we're actually going to pi over 2. And as theta goes to negative infinity, we're actually going to a negative pi over 2. Or x, doesn't have to be theta. But so realize we can have limits that are not exactly the same as we go to positive and minus infinity. So let's go ahead and look at, well, not look at, let's go ahead and state this definition, because I know how much you guys like definitions and your day just wouldn't be complete without it. So definition. So if f of x, so how do we define this idea of f of x, of my function having a limit as x gets really, really big? But let's just describe this. Oops, sorry, I'm on the wrong definition here. Okay, so if f of x becomes arbitrarily close, again, I don't love that they haven't done the formal definition of the, excuse me, I shouldn't try and spell and talk at the same time. Arbitrarily close. What does that mean, arbitrarily close? What does that mean? Whatever, I'm over it. Can you tell I'm over it? Arbitrarily close to a finite number. Let's just call that finite number L. If it comes arbitrarily close to a number, finite number L for all sufficiently large. Again, what does sufficiently mean? Whatever. So remember now, instead of thinking about my x is getting closer to a number, we want to talk about what happens as x gets really, really, really big or really, really big negatively. So sufficiently large and positive. So this is going to be the definition as x approaches infinity. Positive x, we write, so if f of x becomes arbitrarily close to a finite number L for all sufficiently large and positive x, then here's what we write. The limit as x approaches infinity, right, of f of x equals L. Okay, and that's what we say. We say the limit, aren't these colors cool, of f of x as x approaches infinity is L. So sometimes it's, you know, I think I take for granted sometimes because I live in my math world, which is an amazing world to live in, that you guys know how to actually say that, but we just say the limit of f of x as x approaches infinity is L, okay? So in this case, a couple notes here. In this case, we say that the line, so instead of a vertical line like a vertical asymptote, now we're defining a horizontal asymptote. So we say that the line y equals L is a horizontal asymptote. Oh man, I hear my son, he's coming. Asymptote of f of x. Okay, remember horizontal asymptotes, you can cross horizontal asymptotes. Don't believe that person that told you that you can't cross them. We can cross them. But that's what we mean by horizontal asymptote. Again, if you've ever, you know, any of your algebra teachers probably described those, hopefully they described those horizontal asymptotes as describing the end behavior of a function. All right, so the limit, let's talk about if x goes to minus infinity. The limit as x goes to negative infinity of f of x equals L is defined similarly. Innocuously, I can't do that. I'm going to say similarly. I don't even know if that's spelled right. I haven't had enough coffee, you guys, and my son hasn't been sleeping, so, you know, who knows what I'm going to tell you today. So, that's it. So if we go to x equals minus infinity of f of x equals L is defined similarly. Again, if this is true, if this number here exists, then that would be a horizontal asymptote as well. Now there's one other thing that could happen here. What if my function doesn't get closer to a number as x gets large, or as x gets large negatively? So I also want to, let's just define that right here. So I guess we had a couple definitions. Oh, sorry guys. So that's my first definition, and I'm kind of going, I just want to get these definitions done, and then we'll do a bunch of examples. But the other thing that could happen is my function doesn't actually get closer to something. Like if you look at like x cubed, right? Here's x cubed. As x gets as x goes to positive infinity, my function values are also going to infinity. Or as x goes to negative infinity, my function values are also going to negative infinity. So we don't always have to have something that that goes to a number as x gets really big, but we can still talk about the behavior of the function again. So second thing that could happen as x goes to infinity, and this is kind of a mashup of our definition from the last section, but if f of x becomes arbitrarily large as x goes to infinity, or I guess we could say as x becomes arbitrarily large, because now we're trying to define what, anyway, as x becomes arbitrarily large, then we say that the limit as x approaches infinity of my function is infinity, or it could be plus or minus infinity. So we have similar for, I'll put similar, I'm running out of room. So what else could we have? Well, what if we went to infinity, but my function went down, like I had a negative x squared? I could have, so x going to infinity, but my function value is getting really large negatively. I could have, oh, I'm really pushing my luck here. I could have as x goes to, minus infinity, this is exciting, of f of x equals positive infinity, or my last one, what if x goes to minus infinity and f of x goes to minus infinity also? Sorry about that. So those are all kind of the same. Should have thought about that before I start writing. Same definition, right? F of x becomes arbitrarily large, or f of x becomes arbitrarily large in the negative value, or its magnitude is negative. So let's look at a couple. Examples, right? That's what we want to do. So what about? Oops, I always do that. I know that's probably the first time you've watched my lecture, but but I always end up doing that. So let's look at some examples here. So what about the limit as x approaches infinity of, let's say, 3 over x squared minus 4? Okay, so 3 over x squared minus 4. So I can absolutely take, look at the graph of this, right? X can't be 0, but I could look at some values of x. I could look at x being 1, 2, 3, 4. But let's just kind of look at this analytically and see what's going to happen as x gets really, really large. So one thing I want you to notice is as x gets really, really large, this negative 4 is just going to stay negative 4. It doesn't care what x is doing. So no matter what x is doing, this minus 4 is just going to stay minus 4. This guy is the one that we really want to look at. And this is going to be kind of the key with most of these. What happens to 3 over x squared as x gets really, really big? Well, remember what we talked about on Friday. I have a relatively small number. 3 is relatively small. If I start dividing it by really, really, really big x values, I'm going to get 3 over like 1,000,000 squared. Guys, that's going to be a really small number. So actually 3 over x squared is going to go to 0 as x goes to infinity. Okay, so if that's going to 0, then what's going to happen? Well, this guy here, right, is going to 0. 4 doesn't care what x is doing. 4 is a constant. It's going to stay that way. So I basically get 0 minus 4, or I get a negative 4. And I want to show you the graph of that so that you can see that that is going to be true. So if we put this function in, y equals 3 over x squared, okay, minus 4. So as you can see, as x again approaches infinity, this is 4 right here. So there my function is getting closer and closer to 4. It's happening on the left-hand side too. As x negative 4, excuse me. As x approaches minus infinity, then I'm also going to negative 4. I hope that kind of makes sense. And we'll talk about like ways to, well, that's just true. We're going to talk about other kind of things that we're going to do to find limits. But let's look at another example. Let's look at the limit as theta goes to infinity. This is a classic one, sine of theta all over theta. So sine of theta over theta, I can't really put in infinity. You'll kind of see that if you look at the behavior of sine, so let's see what sine does as sine goes to infinity. So sine, oh, that's a beautiful graph of sine. As x goes to infinity, or theta goes to infinity, look at what sine of x is doing. It's basically going from 1 to negative 1, and it's just going to continue going from 1 to negative 1, 1 to negative 1, 1 to negative 1, and I look at my function values. So I can't actually describe the end behavior of this function with just a number. So the limit as theta approaches infinity of sine does not exist. And that's going to be true for sine and cosine. That guy does not exist, okay, because it's not getting closer to a number. And then if I look at theta, as theta goes to infinity, what happens to theta? Well, it's going to infinity, okay? So what I'm going to use here is the squeeze theorem. So let's look at the squeeze theorem. The squeeze theorem is such a useful theorem. So how do I know how to use the squeeze theorem? Because sine's involved. That's how I know. I know the top isn't going to anything, but maybe even because it's being sandwiched between negative 1 and 1, like maybe that bottom's growing fast enough that something's going to happen. So here's what the squeeze theorem does. I know this is the first thing I'm going to state. I know that the sine of theta is always going to be between, no, not negative 1 and 1. That's ridiculous. I can't believe I wrote that. Negative 1 and 1. And now what I'm going to do is divide everything by theta. Now you have to be a little bit careful when you're dividing by things, you guys, especially with inequalities, because with inequalities, remember that sign, the inequality sign will change depending on if theta is positive or negative. But remember, I'm looking at this limit for theta being really, really big in the positive direction. So I actually don't have to worry about like flipping that or anything because I know that theta is going to be positive because I'm going to positive infinity. Now we know that the limit as theta approaches infinity of a negative 1 over theta. So look at what's happening here. Theta is getting really, really, really big. 1 on top is pretty small compared to, you know, a million. So I have 1 divided by a big number. That's a really, really small number. And if you want to put a negative 0, you know, negative 0 is just 0. But that, what is also equal to 0? That's also the limit as theta approaches infinity of 1 over theta. So remember what the squeeze theorem says. The squeeze theorem tells us if I know that this guy goes to a number and this guy goes to the same number as theta, or x approaches the same thing, which in this case is infinity, then that means that the middle. So thus, or therefore, I'm going to give you some notation. If you've ever seen this little triangle of dots, I have no idea why. That means therefore in mathematics. I don't know. Thus, or therefore, the limit as theta approaches infinity of sine of theta over theta is also going to equal 0. Whoa. So let me show you a picture of that. Let's see kind of what happens. Let's go to Desmos. Again, if you don't have a graphing calculator, you guys have to get maybe like the Desmos app on your phone or something like that. But if we look at 1 over or sine over x, or theta, you can see that, yeah, I actually have a horizontal asymptote of y equals 0. And look at, guys, that this graph is crossing it. It's crossing it an infinite number of times, right? And as I drag this out, as x gets bigger and bigger to infinity, you can see there's less and less difference between the graph and my axis. And you can really see that as we go back. And you can see that also in the negative direction. As I look as theta gets very, very large negatively, we kind of have the same thing going on. So just to reiterate a little point here that we had, you know, mentioned in the definition, up here, this negative 4, that's going to be a horizontal asymptote of my function. And remember, that's a horizontal line. So that's y equals negative 4. Here, this guy also is going to have a horizontal asymptote, because as I go to infinity or minus infinity, I see that my functions are getting closer and closer to a value. So we have horizontal asymptote up top here, and we have a horizontal asymptote with this function here. Okay, but we don't always have horizontal asymptotes, right? Our function can get bigger as x goes to infinity. So let's look at a couple of those. So let's look at what happens when, for example, what about the limit as x approaches infinity, right, of something like x squared plus 1. So, I mean, just looking at this, I don't want you to overthink these too much, but we're going to infinity. Infinity is positive. I'm taking a positive number, I'm squaring it, and I'm adding 1 to it. So think about what happens when you take a really, really big number, like a million, you square it and you add 1. That number is just getting bigger and bigger and bigger and bigger and bigger without bound. So this is going to be infinity. Likewise, what if I took the limit as x approaches negative infinity of x squared plus 1? So again, if you look at this guy, what happens when I square a really big negative number? I'm going to get a really big positive number, right? Because I'm taking a negative a million, I'm squaring it, so the negative goes away, and I add 1. So I'm still going to infinity. And the graph of this function, remember, x squared is a parabola opening up, and that plus 1, what does that mean? I just shift it up 1. And so what is this going to look like here? As you look, as x gets really, as I get more and more to the right in my x values, I would have to jump all the way up here to find y values. So my y values are going to infinity. Same thing as I go x in the negative direction, my y values are going to infinity. Let's look at another example here. What if I was looking at the limit, though, as x goes to infinity of, let's say, x cubed? Okay, this is also going to infinity. Right now I'm just cubing really, really big numbers, so that's, I hope that's pretty obvious. As x gets large, what happens when I cube large numbers? I get large numbers. But what about as x goes to minus infinity for this guy? Well, think about, guys, you have a negative number, a really large negative number. Anytime you cube a negative number, you get another negative number out. So what you're getting here is you're getting really, really large negative numbers. So that's actually minus infinity. And again, if we look at the graph of x cubed, and on Tuesday, I hope to go over some of these graphs that you might not remember kind of what they look like, and we'll put them in our notes. But so look as x, as we look out this direction, what's happening to my y values are getting huge. As I look as x goes to the negative infinity, what's happening to my y values are getting really large negatively. Some other stuff that can happen. What about the limit as x goes to infinity, let's say of 1 minus x squared now? Instead of x squared plus 1, let's look at what would happen if I had 1 minus x squared. So but if we can just look at this even without the graph, let's think about kind of what's going to happen. Excuse me. So x is getting really, really big. So you're plugging in those x values in for this x right here. When you square those become positive. But then look at what's happening right here. Then you're making them negative. And then basically you're adding 1 to them. So you're taking positive big numbers and making them negative, and then you're adding 1. The 1's not going to do much. So what is 1 minus really, really big numbers? It's going to be a really, really big negative number. And it's actually going to be the same as we go to minus infinity. So as x goes to minus infinity for this one, I have 1 minus x squared. Remember that squared happens first. So when I put in really big negative numbers, I first square them. I don't take the opposite of them. I first square them. They become really, really big positive numbers now. And then I'm taking 1 minus a really, really big positive number. That's going to be a really big negative number. So we're going to go to minus infinity for this one also. And if you look at the graph of this, what does that negative do? That negative takes the parabola and it reflects it, and then it shifts it up 1. So actually the graph of this guy looks like this. So it makes sense. The end behavior of this function makes sense. As I approach infinity, we're going to minus infinity. As I approach negative infinity, we're going to negative infinity. Let's look at what happens if we flip the x cubed. And this x cubed, I could have like added 1 to it or subtracted 1 from it. Doesn't really matter. So as I look at the limit as x approaches infinity of a negative x cubed, let's think about what happens here. As I approach infinity, right, this guy right here is positive. When I cube it, it's going to be positive, and then I'm going to take a negative of it. So I'm going to take the opposite of a lot of positive numbers. So this is actually going to be a minus infinity. There's Leo. Can you say hi? Hi, he's waving at you guys. So then let's look at the other one. As x goes to a minus infinity, I know, of the negative x cubed. Okay, so same idea here. As I put in a negative number here and then I cube it, remember that happens before that negative in front. This guy right here is going to be negative, and then I'm taking the negative of a negative, which we know is a positive only. In mathematics, 2 negatives make a positive, and so we get infinity. And again, if you look at the graph of this, let's get rid of that guy. If I look at the graph of this, so x cubed looks like this. If I put a negative, basically it just reflects it about the x-axis, and I look like this, kind of should go through the origin. But as you notice, as x goes to minus infinity, the function values get really, really big. So that's why we're at positive infinity. Then as x goes to positive infinity, we go to minus infinity. So those are some examples of what happens when I'm taking the limit, the infinite limits, limits at infinity, well, infinite limits also, of some of these polynomial functions. And so what I want to do is I want us to what I am going to do is I'm going to look at this a little bit more generally, and then we'll write this all down in a theorem. So this again is describing the end behavior of a polynomial. So for example, if I had a polynomial p of x, let's say, and let's just say that p of x is a sub n x to the n plus a sub n minus 1. This is like the general way that we describe a polynomial, dot, dot, dot. We don't know how many terms, so we do the dot, 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 you know. A sub 3 would be the coefficient for the cube term, and some of these a's can be 0, that's fine. X squared, so you kind of see what we mean, and then a sub 0. So these a's are my coefficients, and then this is a polynomial of degree n. So when we look at something like this, when we go to find the end behavior, so if you look at that, oh, I just erased it, darn it. I shouldn't have erased what we had. But with the x squared and the x cubed, right? When I was looking at those, like with that x squared minus, or 1 minus x squared, or the x squared plus 1, the thing that really determines the end behavior of a polynomial is going to be that leading term, or the term with the largest coefficient, okay? And if you notice, why is that true? Well, look at what I'm going to do. I'm going to actually factor out an x to the n from all of this. If I factor out an x to the n, factoring out is the same thing as dividing. I would just be left with a sub n right here. If I factor out an x to the n here, n minus one of them will cancel, right, with the x to the n, and I'll have one left over. So that a sub n minus 1 would be on top, and I would just have 1x left over here because I'm 1 away, right, from n. So the top has 1 less x than the denominator has. Then plus dot 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 plus, right, and I would divide all of these by x to the n, so I'm just going to go to the end here, x to the n. And what happens then, as we take the limit, as x approaches infinity, plus or minus infinity, let's put that. As x approaches plus or minus infinity of this guy, okay, of p of x, if you notice what happens here, this guy goes to 0 because look at, I have just a constant now divided by really big terms, those go to 0. That guy goes to 0, and really we just get the limit as x approaches plus or minus infinity then of what? A sub n x to the n. So this is the guy that's going to determine if we're going to positive infinity, negative infinity, anything like that. So that's when we're talking about end behavior of a polynomial. That's what really is going to drive that is this leading term. And then whether this is positive or negative, that's going to determine a lot of things. And then again, whether this is even or odd, that's going to determine some things, because we know even functions do something like this when it has a positive coefficient. And we know that odd functions, if you remember this from algebra at all, do something like this when it has an positive coefficient. If the coefficient is negative, all that does is it changes the end behavior to look like this, or it changes the end behavior to look like this. All of that. So let's write this down kind of in a theorem. Not kind of. Let's write it down in a theorem. And then we will do some examples. Okay, so there are some pretty important things about, so let's let n be a positive integer. And then we just need to do a bunch of examples, and we got to talk about some rational functions. And let p be the polynomial that we just described a minute ago. All right, so that is p of x, right, is a sub n to the x times x to the n, plus I'm being really lazy, plus dot dot dot. Let's just do the last two. Okay, so it's a polynomial of degree n, okay, where a sub n is not equal to 0 because we just want it to be that degree. Okay, so a couple things here. I'm not going to prove these, but we're just going to kind of tell them they're true. The limit as x approaches either positive or negative infinity of x to the n is going to equal infinity when n is even. And notice I don't have any, if I had an a sub n in front of this, then if that a sub n was negative, it would be negative infinity. But no matter if I'm going to positive infinity or negative infinity, when n is even, anytime I take any number, positive or negative, to an even exponent, it's going to be positive, you guys, to the 4th, to the 6th, squared, anything. What about, oh, sorry, let's get rid of that really quick. Okay, so what about when it's not even? What about when it's odd and I don't have an exponent in front? So, Sarah. So what if this is x to the n? If it's odd and I'm going to a positive infinity, this is going to be a positive infinity. And if I'm taking the limit as I'm going to minus infinity, of x to the n when n is odd, this is going to be a negative infinity for n being odd. Okay, because when I take a negative number and I raise it to an odd power, right, I'm going to get another negative number out. Okay, this one is the most important one, I think, of all of this. When I take the limit as x approaches plus or minus infinity of 1 over x to the n, which we can also write x plus or minus infinity, x to the negative n if you would like, that's going to equal 0. And I've kind of talked about that a little bit, but remember when I have like a relatively small number like 1, it doesn't even have to be 1 on top there. It could be like 4 or 17 or any constant. Really, I've seen this written with like a k on top here. So if you have k over x to the n, that guy's going to 0. That's a big, big deal. And then this is just rewritten with, remember, a negative exponent tells me either puts it on the bottom or brings it up top. And of course that n is positive or negative. It doesn't matter. Okay. And then this last one, which we kind of just proved already, if I want to take the limit of that polynomial, really it's just going to behave. Oh, I should have an infinity there, sorry. It's going to behave just like the leading term, a sub n. And we kind of prove that, right, by dividing everything by that x to the n, okay? And then this is going to actually equal positive or negative infinity. Any polynomial is going to positive or negative infinity, depending on, okay, depending on the degree of the polynomial, right, of course, which if it's odd or even, and the sign of a sub n. Okay? All right, let's do some examples. I'm gonna actually leave that up. I'm gonna be smart this time. I know I am. I can do this. All right, so let's see what we got. So let's determine the limits of as x approaches infinity and minus infinity of these polynomials that we're going to write down here. So what if we had 3x to the 5th minus 4x squared plus x minus 1, okay? And I want to find the limit as x approaches infinity and the limit as x approaches minus infinity. So when I take the limit of this, remember it's only, the polynomial is going to behave like the limit of the leading coefficient. So just going to grab the leading coefficient then, and I'm going to think about this. So, you know, you guys, you are welcome to memorize this. And sometimes it's going to be important to memorize things. You're welcome to memorize all of this. Number 3 for sure. You really need to know that this guy goes to 0. That's a big one. But the other thing you could just do, and I know I'm asking a lot here, but you are in college, is to think about it a little bit. I know that's a lot. So let's think about what's happening. We're taking positive infinity, so we're taking really big positive numbers. When I raise them to the 5th power, they're going to stay positive. And then when I take a positive number and multiply it by a positive number, we stay positive. It's always good to stay positive. So we go to positive infinity. Likewise, the other way, now I'm going to get a little bit lazy here. As I go to minus infinity of p of x here, this is going to be the same as taking the limit of just the coefficient, or excuse me, the leading term. Leading term is the term with the largest exponent. Look at what's, again, think about this. You don't have to memorize those things. So here, as I take a negative numbers, these are all negative numbers, right? As I raise it to an odd power, okay, it's going to be negative. Any negative number raised to an odd power is negative, times a positive is staying negative. So we go to minus infinity. And you can graph these and you can see that that's true also. I know the end behavior of this. It's not going to look like x cubed. It's going to be x cubed, you know, going this way. And it could be doing some crazy stuff, right? I don't think it does all of that, but eventually, this is all the middle part. But what's the end behavior? We're going to minus infinity. Why did I flip it? I'm so sorry. I shouldn't have flipped it. I don't know why I flipped it. It's not flipped. When would it be flipped? If that was a negative 3, I'm so sorry. So it's going to look like x cubed, might do some weird stuff in here, but eventually it's going to do the same end behavior as x cubed. Minus infinity as x goes to minus infinity, positive infinity as x goes to positive infinity. I hope I'm not confusing you too much. I mean, my goal is to confuse you a little bit, right? That's what math teachers do. So, all right, so q of x, let's look at q of x. What if q of x was 4x cubed minus x minus 16x to the 4th? So again, let's look at the leading term of this. So the limit, again, the leading term, remember, is the term with the largest exponent. So the limit of q of x, I can just say, is the same as the limit of the leading term. The leading term in this case, ooh, I kind of tricked you, right? Leading term is this guy. I know I say leading term, and the reason we call it leading term is if you rewrote this in descending order, meaning you're going to put the largest exponent term first, and then go descending order, that would be the first one. But okay, again, I want you to think about this. Think, people, think. Okay, I'm putting in positive values for x here. Apparently, I don't know why I say positive, positive values. So those are going to be positive. I'm raising it to the fourth, so this whole thing is going to be positive, right? Because anything to an even power is positive. But now look at, guys, I'm multiplying it by a negative number. So positive by a negative, we're going to minus infinity. I'm going to take these huge numbers to the fourth power, and then I'm multiplying them all by a negative number. We're going to minus infinity. The limit as x approaches a minus infinity of q of x. Even ones are going to be the same. But let's make sure that that's true. Why are the even ones, the two, going to be the same? Because with that even exponent, no matter what, I'm going to have a positive number. So again, let's think about this. Yes, I'm plugging in negatives in for x here, but then I'm raising them to the fourth power. So this whole thing is going to be positive. And then a positive times a negative. What do you know? We get a negative. So minus infinity. Again, this is to the fourth power. So I don't know what's going to happen with this. I know it goes through the origin, but then I don't know anything else. But maybe it does something like this. I don't know, guys. That's probably not true. You can open up Desmos and look at what's happening. So it can do a little bit weird stuff in here, but it looks a lot like x squared when it comes to the end behavior of it. Okay, I hope that makes sense. These are pretty fun. Well, fun, right? Fun. It's relative, but that's what we mean by the end behavior of these polynomials. So let's talk about rational functions. I think we just have rational functions to do, and then I want to do a couple more examples, and then we're gonna be done. This is gonna be some good stuff, guys. So yeah, we might have a couple more things to write down, but let's talk about rational functions. So I'm just gonna do one for you. And so what I'm going to say here, I'm going to say use limits at infinity. And anytime I say end behavior, that's really what I want you to find. I want you to use limits at infinity to determine end behavior. And what do we mean by that? We mean what's happening as x goes to infinity and what's happening as x goes to minus infinity. That's what I mean by end behavior, okay? So first, let's look at something like this. Whoops. Sorry, I'm just going to give you the function and then we'll figure out what to do with it. So, so for example, what if I had a rational function that was like this? So 3x plus 4. Okay, so I want to take the limit of this as x approaches infinity, and I want to take the limit of this as x approaches minus infinity. So here's the trick. Are you ready for the trick? Here's the trick. The trick with this guy, okay, is to take the limit as x approaches infinity minus infinity. But it's hard to do right here. I would have infinity over infinity. If I looked at what the top's doing, it's going to infinity. The bottom, it's going to infinity. But that doesn't tell us anything. That's also something called an indeterminate form. So what you want to do with these rational functions is you want to find the x term with the highest degree, or the largest x value that you have in the denominator, because it's the denominator that's really going to influence the behavior of this function. Because the denominator really, if our denominator is growing faster than our numerator, then we're getting bigger numbers on the bottom and we're going to go to 0. If the denominator isn't growing as fast as the numerator, right, the numerator is growing faster, then we're going to infinity or minus infinity. And then finally, what if the denominator and the numerator are relatively growing at the same rate? Then we're going to go to a number. And so what I want to do here, this is always going to be your trick. You're going to divide every term in the rational expression by the largest degree x term in the denominator. And you could take the coefficient if you want. I don't take the coefficient with me, but you could. Okay, you're going to do this for rational functions. Well, rational and, yeah, so any function that is a fraction, basically. So let's look in the denominator. I have 1x, so that's the biggest x term that I have. So I'm going to divide everything by x. As long as I do it to every single term in the numerator and every single term in the denominator, I have not actually changed, I don't know why I did that. I see it. I have not actually changed the function at all. Okay, so I'm going to divide this all by x, and let's see what we get. So I'm going to get 2 minus 1 over x all over 3 plus 4 over x. And this is exactly the same function as this guy right here because I did it to every single term. Now look at you guys, why did I do that? Well, because it's awesome, first of all. And second, now as I look at what happens as x approaches infinity, so as, I'm just gonna be a little lazy here, x approaches infinity, here's what's gonna happen. The 2 doesn't care what x is doing. What's happening to 1 over x as x goes to infinity? You guys, that guy's going to 0. What's happening to 4 over x as x goes to infinity? That guy's going to 0 also. So in this case, what is, ooh, those colors are pretty. The limit as x approaches infinity of this function, the limit as x approaches infinity of this function is 2/3. So we have a horizontal asymptote at y equals 2/3. Isn't that cool? And that's going to be true too for minus infinity. So you can see once I get it in this form, right? In this form right here, this guy's still going to 0 even if x is going to negative infinity. Same thing here, that's going to 0 even as x goes to minus infinity. So we get 2/3 for both of them. It's neat, huh? I know, I love doing these. I think they're super fun. Let's do another one. Let's do a couple more. I know this video is getting a bit long, and I know I'm asking you to watch this before class tomorrow. So I actually think I'm gonna do 2 more examples for you, and then I'm gonna stop this video because I apologize, I meant to get this out sooner, but Leo's 6, so he's very, very clingy to his mom right now. So I'm gonna stop this, even though I'm not quite done with this section, after I do 2 more examples, and then we still have some results to write down about all of this, and so we'll write those down in class tomorrow. Hopefully I'll be there tomorrow. All right, let's divide. Again, I'm going to look for the largest term in the denominator. So here's x cubed. Okay, so x cubed, I'm going to divide every single term by x cubed. I'm going to show you every step here now. You're going to get to where you don't need to do every step. And you're going to get to where you're going to be able to, we're even going to write it down. You're going to be able to look at these things and you're going to be able to see what the solution is. But for right now, for this first test, I want to see this step, okay? And again, I'm showing this step. If you can see what everything's going to be once you divide by x cubed, please go ahead and go to that step, right? That is totally fine. If you do that, let me get some room up here. We'll finish this up here so we don't have to go to a different page. So again, what am I saying? What am I saying? You don't necessarily have to show me this step right here, but you do have to go show me this next step right here. So f of x equals, if I divide everything by that x cubed, I get 1 over x, right? Minus 1 over x cubed. That can't simplify at all over, what do we get? Just 4 right there, plus 1 over x squared. Okay, and then plus 1 over x cubed. Nothing we can do with that guy. So now, as I take the limit, as x approaches infinity of f of x here, let's see what's going to happen. So as I take that limit, look at what happens, you guys. Let me get a better color. 1 over x goes to 0. 1 over x cubed goes to 0. These guys go to 0. These guys go to 0. This 4 just hangs out and b's a 4. It doesn't care what's happening. But basically what I get is I get 0 minus 0 on top, also known as 0, divided by 4. What is 0 divided by 4? That's 0. Same thing happens as x goes to minus infinity. Okay, I'm still going to the 0 on top. I'm still going to 4 on the bottom. So I still get 0 over 4, which is 0. So we have a horizontal asymptote at 0. Y equals 0 is a horizontal asymptote. And tomorrow we will talk about like putting it all together, taking like a rational function and saying find the vertical asymptotes, verify that they're vertical asymptotes, find the horizontal asymptotes, all of that good stuff. Okay, last one. Let's see. So if you noticed in that first one that I did, if you look at the degrees, the degree of the numerator and denominator were the same. In the second one I did, the degree of the denominator was bigger than the degree of the numerator. And so this next one I want to do is the last one where maybe the degree, not maybe, it will be, the degree of the numerator is bigger than the degree of the denominator. So let's look at 1 minus x cubed all over x squared plus x plus 1. Okay, again, what is the trick? You find the term with the largest exponent in the denominator, not in the numerator, in the denominator, and we divide every single term in my entire function by it. That is the trick, because the denominator is the one that determines if we go to 0, if we go to a number, or if the denominator is not big enough to catch up, which is what's going to happen in this one. Then we're going to plus or minus infinity, depending on what we got. All right, guys, so let's look at f of x here. So the numerator, I get 1 over x squared minus x cubed divided by x squared is just x. Okay, on the bottom, I get 1 plus 1 over x. Again, if you can go straight to this guy right here, that's fine, but I do want to see this part. All right, you guys, so let's see what happens. So the limit then, as x approaches positive infinity of this guy. So let's see what's happening as we approach positive infinity. This 1 over x squared is going to 0. This is going to 0. This is going to 0. I get 1 on the bottom. Look at the negative x, right? X is going to a positive infinity. So as I go to a positive infinity, this x right here is going to positive numbers, but then I'm taking the opposite of them. So basically I have like a negative infinity all over 1. So that's just going to minus infinity. I hope that makes sense. And I also divided by x squared, and x squared is always positive there. We're going to talk about that tomorrow in class or the next day. What's going to happen with the positive and negative? It can be a little tricky sometimes. Okay, guys, let's look at what happens as we go to minus infinity. This is still going to 0. This is still going to 0. This is still going to 0 as we go to minus infinity. Here, this guy here is going to be negative, right? Because I'm going to a negative infinity. But then you're taking the opposite sign of those numbers. So I'm going basically on top to a positive infinity divided by 1. Is a positive infinity. If this happened to have been a negative one, let's say I had put a negative x squared down here, then this negative would have influenced that, and I would have been a negative infinity, and that would have been positive. So you have to consider all of your signs that you have when you're dealing with these. All right, you guys, I'm at 46 minutes, and I really need you to watch this. Well, if you're hearing me say this, then you've already watched it. So I know I didn't give you a lot of time. I'm sorry that this video got out kind of late, but that's what happens when you have sick children and that want to be held all day. Thanks for watching this. It's important. In class, what we're going to do is we're going to kind of write down everything we just kind of figured out here with all of the rational functions and what happens when the degrees of the numerator and denominator either are the same or different. One is bigger than the other. What happens? All right. Thanks. That was a good time. I'll see you soon.